So let me introduce you. Um, we're going to take a deep dive into now how concurrent engineering is really done. Just because the product's unique doesn't mean you can't industrialize. So Amutu, welcome you. I'm not even going to try to pronounce your last name. I practiced it, and I know I'm going to butcher it, so I'm just not even going to try. I'm sorry. I don't want to offend you. But Amutu is responsible for defining and developing industry solution experiences for the energy, materials, and customers at Dassault Systems. He has like 25 years of experience in product management, consulting, R&D, and market intelligence. He's been a trusted advisor to customers and organizations in industries ranging from automotive, aerospace, and now the energy sector, with a strong acumen in digital manufacturing and product lifecycle management. He's worked and lived in India, Japan, and currently calls Detroit his home. So we're in good hands here. If you could turn on your screen and share your thoughts with it, I'd appreciate it.
Sure, thank you.
Okay, we can see your screen now. It's all yours.
Perfect. Thank you, Gary. I hope you guys can listen, hear me well too, right?
Yep, hear you just fine.
All right, great. Thank you, Gary and SPS. So modern day factories, as Gary has stated, it's awesome. It's so interesting to watch them hum and function like worker bees. And just like Gary, I had the fortune to visit the Toyota factory in Japan, the Numi factory, the Tesla in Fremont, California, as well as my good old River Rouge plant from Ford. So everything is self-contained. Everything is designed as though they are the best in assembly line efficiency. So thanks for joining us today to talk about this high volume production and how automotive companies do what they do best. So before we get deeper into the automotive analysis, a little bit on cross-industry comparisons, right? So if you look at the chart, high volume industries like aerospace, automotive, in the last 2 decades have digitally transformed, as Gary alluded to, by having a common platform, etc., digitally transforming their engineering, manufacturing, simulation processes to the tune of they are able to get their takt time, as Gary alluded to. Takt time is nothing but the heartbeat of a production process that's humming. So Toyota is able to, Toyota-like companies, Toyota, Ford, and the likes, they're able to shrink their takt time up to 75% the last 2 decades. And cycle time, similar measure in the aerospace industry, they're able to crush them up to 55% the last 2 decades. And as a result, Toyota is able to put out a car every 58 seconds. And a Boeing is able to produce a 737 once in every 8 days. And looking at our capital intensive industry, construction puzzles specifically, so we applied similar routes. We tried our operational excellence, lean transformation. We relied heavy on engineering innovation from a hardware perspective. Then we also implemented some behavioral changes, maintenance procedures, etc. But since 2000s, although the investments went high, complexity of projects grew manyfold, but the ROI and the margins have started going in the other direction. So what can we learn from these digital transformation, and how can we apply, take a book or two from their, take a page or two from their book and apply it to our industry? So let's start with the transportation industry, where I have had the pleasure and honor of working in my previous life to the same employer, by the way. So what you see on the screen is a typical vehicle development process. So this covers a vehicle all the way from a vehicle concept to end customer, a full automotive story, right? So it starts with the concept. You want to do an EV, you want to do a sports vehicle with such and such trim, 0 to 60 in 3 seconds, 4 seconds, come what may, whatever their USP is. Based on the customer demand, they come up with their S&OP, or sales and operations planning, at the very early stages, sort of matching what my customer demand is in the next couple of quarters to a year, and how my supply network is, etc. They balance all this and come up with their S&OP plan. Then the engineering and design folks starts into action, and they start doing their system architecture, vehicle modular architecture. Modularity is key. As you see, I'll use that term several times in this presentation, because they want to produce many models, many options, as Gary saw, as much as possible in the same line. So that is your efficiency. That's how you achieve efficiencies. You could have many common parts, and you could have several commonality between these models. So the more you modularize them and the more you standardize and put them on the same line, the maximum efficiency you can get. And the next step of the process, and I'm not going to be going too detailed into every section of the process, but we will focus on a couple of those key items and even take a deeper dive with some examples and demos on few sections. So these days we know electronics and software is in the car. I mean, basically, Ford started calling it's basically a computer on 4 wheels, right? There's so many millions of code and software that go into the making of a car, as well as the electronic part. And on the right, you see the simulation and various multi-scale, multi-science simulation that has to happen in tandem. I mean, these days, many of these OEMs, like the Ford, the Chryslers, and the GMs, they even have a common group called ModSim. So Mod stands for modeling, your 3D CAD model, and your design, your engineering group, working hand in hand with the simulation group, and thus this ModSim group is formed, and they work concurrently throughout the process. So you will also see the concurrent process working in various phases of this vehicle development. And then you go down, then you integrate your suppliers as the next vector, you do your manufacturability analysis, and so on and so forth. So let's take a little deeper look into the engineering and vehicle development process, right? So I apologize for this complicated chart. So basically, every OEM look for economy of scale. Products are becoming more and more complex, and companies recognize that product personalization is critical to business success. Just like what Gary called, you might want a red color vehicle. I want a sports version of that with the leather trim, with such and such interior, with the best Bose speakers and whatnot. So that is one person's choice. So thus we enter this world of configuration, creating personalized vehicles per customer. So what you see at the middle of the chart is this engineering bill of material that even Gary alluded to at the beginning of the meeting. So bill of material. So engineering bill of material, it's just not about CAD alone, right? So you got to bring in the metadata relating to the configuration, the model, the options, what should be produced when. And at the same time, you don't want to be creating data duplication. You don't want to be creating data silos, right? So as much as possible, we need to represent this information in one common structure, but it's configurable and it's shareable, so on and so forth. Model-based system design is a term that you see that you hear a lot in automotive as well as aerospace industries. What does it mean? You want to model what you want to create, right? In 3D, in a common data structure, and you also want to model how you want to create that bill of process, or we call them manufacturing bill of material. So there's an engineering bill of material to which there's a manufacturing bill of material, which is an answer. And as you can see, the requirements, the functional representation, the logical representation, which is the configuration, etc., of your vehicle, and the physical representation that you see on the right-hand lower corner, which is where the CAD and those designs are built into the same data structure. So now you have a configurable data structure that is not only containing all the information you need, it's shareable across various groups, like the simulation group that you see here. So what you see on the screen, it's basically design and simulation people working in tandem, right? So from a CAD model that was generated, the simulation engineers are able to create a accurate representation of a finite element model. Now they can use that to do crash testing. Not just it tells you the structure, the crumple zone, the various factors that you can test very well in advance before you make even a single part. You can do the structural analysis, your strength analysis, and make sure the human that's riding in those vehicles are safe. Would they be able to take that kind of a jolt, right? So this method of working in tandem, creating your CAE or simulation models in conjunction with design happens very, very early in the process these days, before if any product is built. And the simulation doesn't stop there. You can do multi-physics, multi-dimensional simulation. I just want to highlight one more commonly adopted technique, like the additive manufacturing. A real stock part that you see here, which traditionally used to get into some part of a vehicle, now can be lattice designed. What did we do? We just took that stock part, they just created a lattice network of the same. It does the same job. Performance is not any degraded. It uses the same material in it, but it's much lighter. The so-called light weighting is achieved here. Additive manufacturing, light weighting, and you can do your simulation and stress analysis right on that same model and send that information back to design. Now they can build that according to their design. So this whole concurrently, they can do this work in the simulation group, and the modeling group can work hand in hand before even you get into the manufacturability analysis. Concurrent engineering at play. Now I want to enter this other my interest and passion is the digital manufacturing. How a manufacturing engineer, manufacturing planner work in tandem, work in conjunction with the design and simulation group. So a good production system has to have, it has to intersect all these various axes of production problems it's thrown at it, right? So what you see horizontally is like a PLM axis, we would call. Basically, the designer comes up with this engineering bill of material with the right configuration, model, etc. that needs to be built. The manufacturing person picks that up, or planner, or manufacturing simulation engineer builds their manufacturing bill of material or bill of process, account for the same configuration, effectivity, etc. And they send that information to the shop floor. That's one axis. The other axis you can think of is like a person walking into a shopping mall these days and ordering a Tesla. It just comes in, the order comes in, the ERP system picks up. A good modeling or production system tool extends the capability of an ERP system and comes up with the right production plan, the right production schedule. who has to do the job, which tools I need to use, etc., which sequence, and so on and so forth. Sends that sequence, adjusted, optimized sequence to the shop floor. Then, as you see, the automotive and aerospace industries work with various tiers of suppliers, and they bring their parts in. Many times they have to make a decision of should I make or should I buy. So whatever items they don't want to make in-house, they end up buying. Like if you look at 787, Boeing 787, majority of their systems, subsystems, and parts are outsourced. They just have in Everett, Washington, they just put all these final assemblies together in what makes a nice plane. So a good production system ideally should do all these on a single platform, a single digital platform, as Gary alluded to. And if we can do the whole thing from design, from simulation, manufacturing, all on the same platform, it's much more powerful. So how do we do that? The production system part of how do we do the digital continuity, right? So we layer our manufacturing or production system over 4 subcomponents. So we model, we collaborate. Collaboration, you already saw, the whole vehicle development process is a collaborative endeavor. So modeling could be the physical representation of the line that is building your product. It could be a welding line, could be a paint line, could be a door subassembly line, so on and so forth, or the final assembly line where everything comes together. And on the right, you see an optimized plan sequence, optimized for a particular variant that you're building. And the rubber hits the road when you do the performance of this, when you execute these activities or processes that are laid out much ahead of you, upstream rather. And the real power comes in when you can not just simulate and model a resource, which is a tool, a robot, a fixture, etc., but when you can scale that up to a work cell level, to a line level, to an enterprise, an entire plant, entire value network, if you can model, optimize, and execute them in a single system of record, then that gives you the maximum efficiency as well. So moving on, let's take some examples of how a typical automotive industry takes benefit from a fully functioning, in this case, a line. So here, in this example, we see a production system that's building, driver's car seat. And you see various machines working in tandem. You have your robots, you have your material conveying systems, you have the human, etc., etc. So using tools like a factory flow analysis, you can study a machine's KPI, a human's KPI, a robot's KPI, and you can look for bottlenecks, and you can analyze various failure rates, if you will. MTBF can be analyzed, mean time between failure. And what happens when a machine breaks down? What kind of an inventory you'll be building up, and what will you end up with when it comes to a broken resource or a temporarily shut down resource? How can you reroute your production operation? So all these types of what if analysis can be done well in advance without stopping a line, so that when you make your first product, I mean, you see there's a red coming up, basically a machine failed here, and you can do various analysis, like from a resource perspective, from a conveyor perspective, from an inventory perspective, what is your cost? So moving on from a subline, from a smaller level scale system, you could also think of doing that in a much higher, full-fledged plant perspective. So all the pictures and the videos that you see here is the work created using software. So they might look pretty, but right now it's showing a final assembly line with the interior panels and the seats being assembled and the steering column. And although they just look pretty, it is talking about how to do your trajectory analysis, a collision-free path plan. What happens if this one robot starts working with the other robot? Would I collide with the other robot? And what is still my optimal sequence? And physical world collision can be very, very, very expensive. And not only that, we can program these robots digitally. So doing all that work on the same system brings efficiencies. And without stopping a line, you could do a complicated engine mount assembly or e-motor assembly, which is usually a difficult thing to do by a human, and it's heavy, it's not reachable, etc. You can extend those type of analysis to a humanoid, a human ergonomics here, for example. You can look at what they view. You can get that vision. Is it accessible? Is that under EULA regulations? Are they over fatigued? What do they see, etc., etc. All those analysis can be done right in the system. And as you see, nothing is done perfect first time, right? So here we are showing a change process. So a bracket needs to be swapped out because of some various reasons. Manufacturing asked me to change it, and now we are changing that. So a new bracket is changed. If you, as long as you work in the same system, now you can do the impact analysis in a manufacturing bill of material. What you see here in these tiles are these manufacturing little stations and processes and activities represented. And you can take it down further to an assembly context that we just saw earlier and see what is my impact and how do I respond to this change. And all these things happening virtually, digitally, very well in advance. And you can extend that to your machining, your 3-axis, 5-axis machining, be it additive or the traditional machining shops. So basically, with such a digitally connected modular system, with many virtual runs in advance, you are still able to get a good quality product the first time, most of the times. So and you can scale. And jumping on a little bit from a McKinsey report that recently saw, just to summarize, we can do something similar in the construction industry. And you can think of cycle time, like an operation science principle. And this report also called for, it is time to bring in this productivity and data visibility issues together and try to unlock these efficiencies by integrating them together, preferably on a common platform, so that the further growth of these technologies can be made easier. So just to, before we depart, summarize, digital information has really helped the automotive and aerospace industries to achieve what they have done so far, and they keep extending that using simulation, manufacturing, and various analysis in a same platform, in a same tool, ergonomics, etc., brings you much more benefits, like automotive has done time and again, and they still want to be improving more and more. If you do them on a single platform, it is still much more effective. So just a bit of legacy, who we are. I work for Dassault Systems. So we were known for our PLM products and what we digitized, and we did a DMU of the first Boeing aircraft to Toyota, to Ford, and then Tesla, and all modern EVs use our software to do their validation. But more than that, in the last 8 years or so, we also brought everything together into a single experience platform called 3D Experience Platform, where we are able to serve not only the high volume industries, but also other growth industries like the energy industry, the life sciences industry, and so on. I started applying my digital manufacturing principles into my energy and materials industry customers. I'm really passionate about, and really thank you SPS and Gary for this opportunity. Thank you.
Well, thank you. Boy, that always gets me jazzed up every time I see what's possible. And I just have no doubt what you laid out there is the way of the future for the types of things that we're involved with in creating. The idea to be able to virtually construct something and ring it all out, sort out how we're going to do the work well in it, before we ever cut a piece of steel. Wow. I think we'll get huge efficiencies. So thank you very much for taking the time to give us that presentation.